All right, we're on Unit 3 now, which is all about triangle congruency or finding congruent triangles. Section 1 is about congruent figures. So not just triangles, triangles is the main thing, but congruent figures overall. So the first thing we want to look over is regular polygons. And this is one of your vocab terms here. I want to have this one written down. A regular polygon is a polygon, or again, like a figure. So it's just an enclosed shape. A polygon which has all sides and all angles equal. So a regular polygon that has three sides. Remember, a three-sided polygon would be a triangle. A regular triangle is what we call equilateral triangle. Okay, we would say all sides are equal to each other and all angles are equal to each other. Okay, if we wanted a regular polygon that had four sides, that would be something we call a square. All of the sides are equal to each other. All of the angles are equal to each other. It's kind of nice because we know for each of these we can figure out exactly how big all of those angles have to be. For a regular triangle, they all have to be 60 degrees. For a regular quadrilateral or regular four-sided polygon, they all have to be 90 degrees. They each have to be a right angle in a square. Okay, and we can do this for any regular polygon, but just the term for a regular polygon means a polygon that has all sides and all angles exactly equal to each other. When we're looking at interior angles of a polygon, so if we had like a triangle, the interior angles are again all of these angles on the inside, and we can find the sum of all of the interior angles, so adding up all of the inside angles together using this formula, 180 times the amount n minus 2, where n is the number of sides of the polygon. So before we said we know for sure that for a triangle, all of the angles have to add up to 180 degrees. Well, let's see if that holds true with our formula here. We'd have to take 180 times, how many sides does a triangle have? 3, that goes in for n, minus 2. Check and make sure that works. Well, 3 minus 2, that'd be like saying 1. So 180 times 1 is actually 180. So that one holds true for triangles. That one fits. Let's check for squares. We know that for squares, they have to add up to 360. So we have 90, 90, and 90, or 90, 90, 90, 90. We have 4 of them. So again, we just plug it into our formula. 180 times however many sides there are, 4 minus 2. Okay, this should be the total. If we add up all of our inside angles, any square, or actually any quadrilateral, anything that has 4 sides, all of the angles should add up to this amount. Well, 4 minus 2 is going to be 2. We're still multiplying it by 180. 180 times 2 is 360. 360 degrees. So anything that has 4 sides, any polygon, so any quadrilateral, will have 360 degrees if you add up all of the angles on the inside. Okay, so going on to examples using this fact, what's the sum of the interior angles of a hexagon? Hexagon, hex means 6, so if I had something that looks like this, we have 6 sides here and 6 different angles. Okay, if I wanted to know the sum of all of them, if I added up each of these angles, how big would I have? Well, I'd have to plug it into my formula. Say 180 times 6 minus 2, I have to use 6 right here because it's a hexagon, is going to equal my whole sum of all the interior angles. Well, 6 minus 2 is 4, so 180 times 4 is the sum of all of the angles. And 180 times 4 is actually 720. So 720 degrees is the sum of all of those interior angles. Okay, if I were to add each of these angles, this one this one, this one, this one, this one, and this one. If I added up each of those, it would have to come out to 720. Example 2. What is the number of sides in a polygon if its interior angles have a sum of 2,520? So let's say we already had the figure. We measured up all of the angles and we added them together and we got 2,520. And we want to know how many sides exactly that figure has. So we're just kind of plugging it in and going backwards. Remember, our original formula said 180 times n minus 2 equals the sum of the interior angles. Well, we know the sum. That's this piece right here. They gave us that one. So we just replace it right there. We kind of substitute it in. 180 times the amount, n minus 2, equals 2,520. Okay? Now, at this point, you might be tempted to say, oh, let's do our distributive property right here. That'll help us with that. Well, actually, because this is saying 180 times this amount, so this times this, we can get rid of it by dividing both sides by 180. So divide by 180, divide by 180 on both sides. That gets rid of this. Because multiplying by a number and then dividing by it, again, it kind of cancels out. So we're just left with this n minus 2 piece. Then 2,520 divided by 180, we'll just have n minus 2 equals 14. At this point then, we don't really need these parentheses anymore, because all it's saying is just that n minus 2. So to get rid of this minus 2, we would add 2 to both sides. When we do that, we'd find out that n equals 16, or there are 16 sides. So if I were to draw some kind of shape, think what it would look like. Something crazy, something weird like that. It would have 16 sides. If I added up all of the angles on the inside of that 16-sided figure, it would be 2,520 degrees on the inside. On our last example for these ones, what is the measure of just one interior angle in a regular pentagon? Well, to help, it might make it a little bit easier if we were to draw a pentagon. Okay, mine's a little lopsided, but this is a pentagon. It's a 5-sided figure, and we want to know just one of these angles. Okay, well, first off, we'd have to find what the sum of all of them is, what that red one plus all of these ones is. If we can find that sum first, then we can figure out just one of them. Okay, so to find the sum, again, we have to start with our formula, the 180 times n minus 2 equals the sum of the interior angles. We know that we're having 5 sides. It's a pentagon, so there'll be 5 sides there. So 180 times 5 minus 2 equals the sum of all of those angles. 5 minus 2 is 3, so we have 180 times 3. And 180 times 3 is actually 540. So if I were to take this, this pentagon and I were to add up all of those angles, each one of these here, add them all up, it's going to be 540. Well, if I know that all of these added up is 540, and I know that there are 1, 2, 3, 4, 5 of these angles, I can just take 540 divided by 5, and I would get 108 degrees. So each of these, again, mine is kind of lopsided. If I drew all of these exactly equal, these would each be 108 degrees. Let's move on to learn about the exterior angles of a polygon. The sum of all of the exterior angles of any polygon, not just certain ones, any polygon, are going to be 360 degrees. So again, if we had like a triangle, remember our exterior angle is one like this, If I were to draw it over here, I'd have an exterior angle. If I drew it over here, I'd have an exterior angle as well. All of these, so at this point, at this point, at this point, if I added up all of the exterior angles, okay, those would all have to add up to 360. Okay, and actually it might be better, it might make a little more sense if we just extended each line only once. So let me redraw that. Say here's our triangle. We're going to extend this bottom one off to the right. The one on the right then is going to extend this way. This line on the left is going to extend down this way then. So none of them get in each other's way. Then this exterior angle, and this exterior angle. If we add all of those up, it has to be 360. Okay, that's what they're saying here. So, again, how can we use that in some of our examples? If the question were just simply what's the sum of the exterior angles of an octagon? So if I were to draw out an octagon, looks like a stop sign, something like that. And I wanted this exterior angle plus this one plus this one plus this one, and all of these added up. Okay, if I added up all of those exterior angles, how big would it be? Well, we know that all of them have to add up to 360 degrees. Anytime we have all of the exterior angles of any polygon, we add them up, they have to be 360 degrees. Okay, so again, if I had just this octagon, and I wanted to know what is the measure of one exterior angle of a regular octagon, so I was just looking for maybe just this angle right here. Well, I know that there are going to be 8 exterior angles. If there's 8 sides, that means there's 8 interior angles. So all of these ones on the inside here. If there are 8 interior angles, that means there have to be 8 exterior angles. And if I know that there are 360 degrees when we add up all of our exterior angles, and that there are 8 of them, I can do 360 divided by 8. So each one is going to be 45 degrees. So this blue piece is 45 degrees. This one is 45. This one, this one, this one. All of these are 45 degrees in a regular octagon. Now we're going to go on to congruent polygons. Okay, so again, what we're looking for, what this is saying is all of these figures or all of these shapes, we would say that this one is congruent to that if they have these things in common. They have to have the same number of sides. Obviously, you can't say a square is the same as a triangle. Okay, it can never happen because they don't have the same number of sides. Okay, the corresponding sides are equal in length. Okay, so if I had like my leftmost side of this triangle and the leftmost side of that triangle, they have to be equal in length if I'm going to say that they are congruent. Now, it might not be the best idea to call them the leftmost because you can kind of tilt them too. I can have this triangle, kind of looks like that, kind of the long piece there, and I can have this triangle. I can say that these are equal because I rotated this one. If I took this one and kind of turned it on its side and make it look like this, these can still be equal to each other. Okay, or they can still be congruent. We just have to make sure that all of the sides match up. Okay, so I couldn't say that this side equals this side. That wouldn't make sense. Okay, that one has to be this bottom side here. So that's what they mean by the corresponding sides are equal in length. They all have to match up and be the same length. Okay, and same thing, the corresponding interior angles are equal. So anything that's kind of, again, in the same spot on each of our shapes, they have to be the same degree measure for our angles. This one is, again, part of your vocab. A congruency statement is the statement which names a pair of congruent figures with corresponding parts matching up. Okay, so it's saying this thing is congruent to this. Okay, and it's really important that we get down the fact that they match up. Okay, and I'll show you what I mean. Let's actually start with this middle one here. If we're looking at these two triangles. Okay, one triangle, we can see it has the spots B, C, and A. The other triangle, we can see it has E, F, and D. Okay, now I can name this red triangle any three of those points I want. I can call it triangle CBA, or I can call it triangle CAB, or I can call it triangle ABC. Okay, I can call it whatever combination of those letters that I want. But if I'm going to say that it is congruent to this triangle, I need to match those pieces up. And here's how that works then. Okay, if I'm going to match those two triangles, I need to make sure that I call the first one a certain thing. So calling this one A, then B, then C. If I'm going to match it up perfectly, or according to our congruency statement, notice how B is the one that has its right angle there, the one that looks like it would be a right angle. Okay, the one that looks like it has that kind of angle is our E. So B and E have to match up. Okay, A looks like it has the smallest angle here, so it has to match up with our smallest angle up here, which would be E. So wherever I have, D. So wherever I have an A, I have to match it with D. Wherever I have B, I have to match it with E. And wherever I have this one, C, that has to match with F. So I'd have to say ABC is congruent to DEF. That is the congruency statement. Okay, when you're matching them up letter by letter. Okay, once you've matched them letter by letter, you can match them as segments. I can say AB, this segment from here to here, is just as big as DE, this one from here to here. Okay, once we have our congruency statement, then we know which ones will all pair up. So now that we know kind of how to do these congruency statements, let's try it with our first one over here, this example. Okay, this green figure, it's again a quadrilateral, it has four sides. It doesn't necessarily look like it's a trapezoid or a parallelogram or anything that we know for sure. It's just a figure with four sides. So we don't necessarily know what to call it, but let's start off by naming it as our quadrilateral LMNO. So we'll start off with LMNO. If we want to say that it's congruent to this yellow figure over here, we need to make sure that each piece is matched accordingly. Okay? Notice how M is the only one that has kind of the bigger obtuse angle. In this case, over here, Z is the one with the obtuse angle. So Z needs to match up wherever M is. So in this case, M is our second letter, so Z has to be our second letter. Our first letter was L, so we need to match L with the one that's going to be, again, kind of right next to this red angle, and it looks like it would be the smaller of the two. It's not quite as big as this angle, and it's kind of the smaller one here. So in this case, it looks like this is our smaller angle. Okay, so L has to match with the W. So when we make our congruency statement, we would say LMNO is congruent to WZYX. Okay, even though alphabetically you would think we'd have to say WXYZ, W, X, Y, and Z don't match up with L, M, N, and O. Okay, again, we said L matches with W, M matches with Z, N matches with Y, and O matches with X. Okay, now if we were to, again, kind of look at our segments, L to M is the same as W to Z. So this one is the same as that one. I could say N to O is the same as Y to X. So N to O, this one, is the same as this one. Okay, so you have to write the letters in the correct order to make sure they match up. Okay, in this last one, they didn't really give us any letters to go off of, But for our congruency then, if we're going to say this thing is congruent to this, we can still kind of match things up by giving the little tick marks. So in this case, this side, we would say, again, it looks like this whole thing has to be rotated sideways to make the same as this. So it would be these two pieces that match up. This one over here then, again, it's kind of on the same side, but two sides away, so it has to match up with this piece. If we do 3 crosses here, that would be this one. If we had maybe 4 right here, we're kind of running short on space, but it would match up with that one. This one, maybe it has 5. We would say that matches up with this one. And instead of doing any more ticks, I'm just going to do a big circle on this one. That would have to match up with this piece. So again, even though it's rotated, we still see that it has to match up with all of the other pieces in our other one exactly. In a piece like this, where we would see that it's not congruent, they look really, really similar. Again, this one we can rotate down and it would look really similar to this piece, but they're not actually the same size. So in this case, we would just say the congruent symbol, like we're about to say that they are congruent, and we just cross it through to say they are not congruent in this case. Okay? In this case, they are similar. They look kind of the same, but one is obviously bigger than the other one. So they are not congruent, they are similar.